So when you combine maybe an s or a 2s orbital together, or an s and a p together, those are different than an s and a p alone. So let's look at some examples. Now, you can follow along on this. This is really a good website. I'm just going to go over those notes. As I was making these, I found this and I thought, you know, this, instead of redoing exactly what this person is saying, I might as well just show it and just go through it with you. But if you want to look at the website, it might be easier at a later time. But I'm just going to go through that right now. We're looking at hybrid orbitals now. So these are for polyatomic molecules. We want to explain the number of bonds formed and the geometries. So again, a hybrid orbital is a mixture. It's a combining of different orbitals. So an sp orbital means that an s orbital and a p orbital are made into something new. So if we consider this dot structure of beryllium fluoride, and the VSEPR, which we just talked about, would predict it would be linear. Now what about the structure? Now let's look at the fluorine configuration, and we have one unpaired electron here in the 2p orbital. Now this can be paired when it's bonded with one of the beryllium electrons. But if we look at beryllium, it has 2 electrons here, and there are no unpaired electrons, and so beryllium in this state is incapable of forming a covalent bond with fluorine atom. But the beryllium could hybridize and promote an electron to the 2p orbital. So notice this electron now went to the 2p orbital, and now it is ready to be bonded. So this would result in 2 unpaired electrons, one in the s and the p. Since these are now available for bonding, we can combine these orbitals. So we combine the 2s and the 2p orbitals, we hybrid them, or hybridize them. They become a hybrid, and that s and p orbital that are combined is now an sp hybrid orbital. So let's look at that. Here's the s, here's the p orbital. When they hybridize, they combine, they make 2 sp hybrid orbitals. It goes around the nucleus. Here's the orbitals that are going around the nucleus ready to be bonded. This is what it would look like. This is what the hybrid orbital would look like. As they combine, they're opening up 2 spaces to bond with the fluorine. So this is the sp in the beryllium atom. And notice this one is, these are empty, but these are now ready to bond. And when we have beryllium F2, BeF2, this is what it would look like. And we have the bonding overlap of the s, or the sigma bonds there. Okay, so you have the sp orbitals 180 degrees linear shape as predicted. Now we just looked at an sp hybrid orbital. Let's look at an sp2 and sp3 hybrid orbitals. Now the sp2 orbital means that's an s orbital and 2 p orbitals hybridized. Not an electron, not 2 electrons as an electron configuration. It means an s and 2 p orbitals, and an sp3 hybrid orbital means an s orbital and 3 p orbitals combined to promote a hybrid. Whenever orbitals are mixed or hybridized, the number of hybrid orbitals is equal to the sum of the orbitals being hybridized. Each hybrid orbital is identical except they are oriented in different directions. So let's look at boron trifluoride. The boron electric configuration we have right here. And what it's going to do is we want to use these 2 electrons and we're going to promote them to the P area. Okay, so that means by doing that, these are open for bonding. Otherwise, if they're here, they're not going to be able to bond. So we promote that, and then we bring the 2s and the 2p together. And we have a 2s, 2p2 orbital. That is hybridized. Now this is ready to go and bond with the fluorine, the 3 fluorines. So we have the s orbital here, the p orbitals, they hybridize, and we get an sp2 hybrid orbital, trigonal planar. Okay, now let's look at an s orbital mixing with all 3 p orbitals to form an sp3. Methane. Now your book talks about methane and how it hybridizes. If we're to look at carbon, the carbon atom has 1s, 2s, and then 2 here. So what we can do, or what the carbon can do, is it can take 2 of these and have 1 in an s and 3 in the p orbitals. So that means all of these are now ready to be bonded, whereas before, in this case, these 2 were not, only these 2. So all 4 here are to be bonded. That's the promotion. And then they hybridize, they come together, the sp, and we make one major bonding orbital, the hybrid orbital, the sp3. Here, s orbital with 3 p orbitals, 1, 2, 3. It hybridizes, and we get a tetrahedral. sp3 hybrid tetrahedral. So it's actually, I think, pretty cool that atoms can do this. They'll combine energy levels. It leaves more bonding area open, basically.